Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois, and this video is going to take a high-level introductory look into the idea of the topic of a binary tree. So, we already covered this. Linked lists, the linked list demonstration. We are kind of developing the same linked list. We have in the linked list idea, we had a forward link and a backwards link. Depends on which way you're pointing here. I'm mirror imaged, so that you can always link to the previous node and the future node from any node inside of your linked list. And so the idea of this kind of is the same, where we're linking to two separate nodes that are not myself. And as you can see in this demonstration here in this graphic, that instead of it being a linear list, it's more of a it's more of a tree structure. It looks more like a tree. I'm staring at a tree right now outside my window, and I can see all the branches branch off, and this branch branches off into two nodes, and so forth and so on. And you can see where the idea of the name tree came from. So a binary tree, it's a nonlinear linked list, yes, as I just described, in which each a particular node can point to 0, 1, or 2 other nodes. So coming back to the linked list idea, if we only had a size 1 list, that one node pointed to 0 other nodes because there was no node to its previous and no node to its next. But otherwise, like the nodes in the middle, if you had a longer list, all the nodes in the middle would point to 2, the previous one and the one in the future. And so, and you can also have one, like the second list, the second one from the front and the second from the back, or I guess the front or the back, depending on just thinking things out. The front, if you had a long list, the front and the back would only point to 1, but all the others would point to 2. So it's like 0, 1, or 2 are the allowable number of nodes that I can point to. And you can see here, this guy here points to 2, this one points just to 1, and then these point to none. And so just like the linked list pointers and the way we set up the nodes, it's going to be pretty much identical. We're going to change the names of it from previous to next to left and right, but the node itself, the structure itself, could keep the same. Like even if I didn't go in and change that, I could still use the same node structure, the same class structure that we had previously. We're just going to use it in a completely different way. Okay, so I said we're going to be using the pointer idea, just like the linked list idea. So we're going to have a link to the head pointer, and it points to and this is where things get a little different here. It's going to point to the first node in the binary tree, and then, so it's tree pointer, head pointer, and then there's going to be a root node, and that's going to be the top of the tree, and then we're going to have, like basically leaf nodes too, that don't point to anything, that are like the end. So it's like they use the terminology of a tree very well here. You got root and node, and then you have like leaf nodes and things like that too. So that's looking pretty good. So here's the leaf nodes that have no children, just as I was describing. I'm always one slide ahead of myself. So the 7 and the 43 nodes are the leaf nodes. The 31 is the root node or the head node, however you want to think of it. And everything in between is, the kind of, how, I don't know if there's a real term for it, but those are the nodes that are both parents and children. So here we go, child nodes. So nodes below a given node. So just because I'm a child doesn't mean I'm also not a parent, right? Like my mom is my parent, and my child is also my child. So I can be both a parent and a child depending on the context, depending on what I'm trying to look at here. So to say this is a pure parent node, or it is not a child of anything else, different from the real life analogy, but everything else, these guys have a parent and have a child, and this one has a parent but no children. So just, where are we going with this? And one thing you may or may not be seeing here is that, like, how are these values organized? You might see a pattern here. And so one thing we're going to see here is that as this data structure gets set up, that organization, sorting of this list occurs automatically. As I insert and remove, if I follow a few certain rules, and some of the rules are obviously easier than others, that the data will come out sorted. 7, 19, 31, 43, 59. It all matters how we traverse this list. And it's recursive, I'll give you that much. That's why we were covering recursiveness last week. And so now we can take a look at making sure that this comes out right every time. So, okay, and then the parent node. So children and parent nodes, again, it pretty much matches up to what we expect with the way we live our lives with our parents and our children. Okay, so any tree can be broken down into subtrees. So it's just a matter of when I'm seeing this and I go, the whole thing is a giant tree, but I can take any node, any particular node, and just say, okay, you're now part of a new tree because it's a sub-tree. And so that's the thing though, like all the subtrees have to add up and make one giant tree. So the rules have to apply at every level along the way that, the rules that we come up with here, so that this thing, this node 31 is a tree. This node 19 is a tree. 7 is a tree. Every node individually could be considered a binary tree, and every step of the way as I combine these things together, I also get a tree structure at the end. So let's see, they're saying 19 and 7 are the left subtree. If you want to think of it, if I start with 31 and I go, just give me the pointer to left and start from there, that is a subtree, and 59 and so forth here is my other subtree, left and right. I'm reversed to you, so sorry about that. I'm terrible with reverse stuff here. So left subtree, right subtree when you're looking straight at it like a piece of paper, I guess. Okay, so again, this is pretty cool in the way the structure sets up. Binary search tree. So we're going to set it up so when we have a value sitting inside of any node, that the left subtree will contain values that are always smaller than this. So no matter what, like we don't necessarily care about the organization over here. We do, but I mean directly we don't care, because this thing is set up a little differently, but every value that is less than 31 will go into my left subtree, and every value that is greater than 31 will go into my right subtree. And so basically think of, if you didn't watch the video, maybe watch the video on quicksort. And so it's like basically the same idea as a pivot point. Like 31, this is sorted, but necessarily everything to my left and everything to my right, it is sorted if it's in a binary tree, but it's not something I directly am worried about. There's the understanding that this is occurring. So every node, every step along the way. So if I looked at 19, everything that's less than 19 is over on the left, and anything that would be greater than 19 would be on the right. But again, so just following the rules, like anything between 19 and 30 inclusive would go into here. Anything that's 32 and above would go over to the right subtree. So again, it all just obeys all the rules here, and everything just falls in, and everything just works if you follow the rules here. So again, left subtree less than, right subtree greater than, and every subtree along the way will obey those rules. So okay, here is the rule. How would I search for a value in the tree? So if I was searching for the value, let's say the 43, what would I do? It's kind of like, it's a binary, right? So just go back, think of a binary search, think of the way binary search works, and the data structure is more complex, but the idea is exactly the same. So I go, okay, hey, are you 43, number 31 here? And I go, nope, but I'm less than the value that you're looking for. So that means I'm going to go to the right subnode because I'm looking for a value larger than the one that's sitting in that node. And so now I go, hey, 59, are you 43? And you go, nope, I'm not 43, but I'm larger than what you're looking for. So now I go to the left. And then you go, hey, are you 43? And you go, yep, I'm in here. And then now you have your node, you have your pointer to the node that contains the item that's the 43. So let's think about trying to find a 22. And so it's the same idea, just like, again, the binary search. Say, hey, are you 22? Nope, but I'm larger than you. So go to your left. And you go, okay, hey, are you 22? Nope, I'm 19. I'm smaller. Go to your right. And then now there's nothing left to search because I've hit a null pointer. And so I've exhausted the search and I go, nope, it is not in here. And so that's the idea. Is it's just an if-else, basically just think of how that works with the binary search. It's just, if I found it, I'm done. Otherwise, try to go to my left, try to go to my right. And if I can't find it after a certain number of searches, and in the binary search, if the left and right pointers have moved themselves around. But in this case, it comes down to, if I hit a null pointer here, then I know I've done something. I haven't done anything wrong. I just haven't found the number. And as long as this thing is sorted appropriately as a binary tree, then I am guaranteed that that value is not found in my tree. So this slide just explains exactly what I just described before. So it's just going ahead, if I'm trying to find 43 again, let's just follow what it says here. Examine 31. You go, nope, 43 is greater, so let's go to the right. And you go, hey, are you 43? And you go, nope, I'm larger, so 43 is less than, so I got to go to my left. And then I found the node. So just as a quick description there, that's how that works. Okay, so what other descriptions are there? Again, the cool part about this is everything is sorted. So the sorting takes place automatically, and I don't have to think, say I insert something into a set, into a binary tree, and I follow the rules, and everything is already pre-sorted. As opposed to a vector where I have to, basically I can put everything in and then I have to call sort to sort everything out. So everything gets organized, binary search tree. Like I say, what would I want to do? Create the tree, of course, like using a constructor. So we will have a video where we take a brief look at this kind of stuff. We'll also have a look at the standard template library, since at the end of the day, that's what we're going to use moving forward in your life. The standard template library, you're never going to reinvent this wheel, but it's always good to know how the data structure works under the hood. So of course, the major ones, I want to insert a node into the binary tree. Like create it is great to create an empty tree, but I want to be able to make sure that every time I insert, whether it's empty or got 600 elements, that it inserts correctly every single time. And then find a node, we already kind of described that one in the previous slides, and then delete. And modify would be another one, but a modify in these cases isn't the same as what a vector uses, because of the way everything is pre-sorted, that if I wanted to modify something, essentially I have to delete it out of the tree and then put it back in with its new value so that it remains sorted after I modify the data stored inside of it. Because just like the binary tree, or I'm sorry, the binary search idea, if the vector that I'm searching or the collection that I'm searching is not sorted, if something's off, then all it takes is one little error, and I'm not going to find data that's perfectly logically found inside of this data structure. But because of the way I've allocated my memory and the way the algorithm works, it gets lost. So I have to make sure in those kind of situations where I'm modifying, I delete what's in there right now, change up, and then put it back in so that it resorts itself. Okay, so again, this looks very familiar to what we did with the linked list. This tree node, I said, if you just replace previous and next in my previous example in the previous videos with left and right, and you're exactly in the same place. And if you just understood, if you just kind of went with it and just said previous was left and next was right, you do not have to modify that tree structure at all. But it only takes a couple clicks, especially in Visual Studio, to rename everything. So I think it makes sense, especially starting out visually, until it clicks what's going on here, to kind of just go ahead and change the names of everything to left and right. And again, I took this and I advanced it a little bit in my video so that we have a constructor, so that we don't have to worry about setting up all the links every single time I want to set up a node inside of these functions, that the constructor sets up the null pointers and sets up the correct pointers appropriately. So again, fall back to those videos if you need help with that, or just wait until we get to the wait till I get to the newer video here. Newer for me, maybe not so much for you, when it comes to using the custom tree that we're going to put in one of the videos. Okay, so this looks pretty familiar, right? So creating a new node is just setting up the two linkages and the data stored inside of it. So if I wanted to put a value inside of it, like value is the member variable for that class, and say, okay, 42 goes into the value. And now the key is, what do we do with the left pointers and the right pointers? So if this thing is a brand new node, just right off the bat, most likely we're going to point to null in both cases, because there's nothing, I believe it's every case here, because it's going to have no children. Because it's especially the first node, right? Because there's nothing to point to. So new node, set the value up and say, okay, left pointer's pointing to null, right pointer's pointing to null. I do not like this notation. There's no reason why you can't just make it 2 lines of code to make it a little simpler. But that's just me. Everyone else has their different ways of doing their code. But okay, so you can say, set up my new node. Notice this is new, right? So we're dynamically generating this memory. So if we're doing this at all, we have to be the ones to delete this memory ourselves. So that's another operation this thing would have to be able to do, is to clear out all the memory, to delete all the memory, so that nothing is left out to memory leaks. So okay, so first step, put the value in, then put the pointers. I like to put the left and the right. They like to put things right after. I like to move this pointer over to the side, just visually a little more appealing. But yes, this is my left node, this is my right node. Okay, so setting up the basic node is relatively simple and very similar to everything we've done before. So now here's the kicker. How do we insert? And again, this is just a high-level demonstration. We'll do more low-level, in-depth demonstrations in future videos. So if the tree is empty, so because that's a key there, is that head node or the root node is pointing to null to start with. So getting this thing going takes a little bit more work. There's a little bit more inertia there than just when you have something in there to kind of work with it. So if the tree is empty, just insert the new node as the root node. So we've already kind of described this. This new node is generated, and we could just say root equals new tree node, and then set up all the values, presuming we have this root node. And again, this is just a high-level demonstration. So if the tree is empty, just go ahead and add it, because it goes from a 0-sized tree to a 1-sized tree. And so otherwise, we have to go ahead and try to find where in this thing we need to go to to put this thing in so everything is in sorted order. So the thing is, a binary tree does not, at least a just pure binary tree, a set, std: set collection, does not maintain duplicate values of items. So you'll see in this demonstration, if there's already a 3 inside my list, that this will not add a second 3 to the list. It'll just fall through, and basically, because a set is a set of numbers that are unique. And we can have a multi-set that does not have that contains duplicate versions of particular values, but that's not what the pure idea of a binary tree, the pure idea of a set is. So I'm just just like the search, I'm going to go left and right, less than and greater than, until, continue comparing. And again, the whole idea is I'm putting a new value. I'm presuming I'm putting a new value in here. So at a certain point, if I try to go left and I try to go right and I hit a null pointer, that is the logical place where that item should go into my new set. And because you're not going to be adding, you're not going to be duplicating a 3, you're going to just go left or right until you can't hit anything. And then that new pointer that the new node that you set up, you jam it into that place. And you set this, you set this null pointer to point to the new node. You'll see here in a second. So as I was describing, if this thing is empty and I'm trying to add a 23 to the list, just have the root point to this new node. But now I have this data structure. Let's see, what are we trying to add here? Let's just say we're trying to add the 22. Let's add a 22 to this data structure. And so what I'm looking at here, I'm at the root, and I say, okay, root is pointing to 31. And I go, hey, is 22 less than or greater than 31? And 31 goes, hey, I'm less than, or I'm greater than you, so I got to go to the left. And just like before, hey, 22, I'm like, what are you? And I go, well, I'm less than you, so you got to go to my right. And then you go, hey, null. And so the 22, this node, or 23, or whatever number you want, that's, in this case, it would go into this pointer would be fulfilled by pointing to the new node that I'm generating. This 23 would go here, 22, whatever value you want to talk about. And so now everything is still sorted because the 22 is larger than 19, it goes to the right. It's less than 31, so it's on my left. So it's maintained the validity of the tree. Like as we discussed, everything less than a node is on the left, everything greater is on the right, and that applies to every single node in my tree. So again, if I try to add another 19, I would say, hey, are you less than or greater than? And you go, yep, I'll go to my left. And you go, hey, are you less than or greater than? And what happens in the way that the structure, the selection structures, the decision structures work is if it's not less than and I don't go to my left, and it's not right, it's not greater than and I don't go to my right, then I don't do anything. I'm done. All of the recursion falls through, and I don't add anything to the list because I don't need to, because it's already found. I thought there'd be another slide to this, but I guess there is not. Okay, so this video shows you that there are many different ways we can actually go through and try to traverse the tree, because a lot of things, like what if I wanted to print out all the elements of my tree? Well, I would probably want to print them out in sorted order. And that's just one of the different ways that we could go ahead and traverse this. So you can see there's 3 different things I need to do. I need to process the data in my node, so like if I wanted to print out my data, go print out my value, or I can go to my left and go to my right. So these are just 3 ways to go about doing things. There, if I can, this is 3 factorial, because I can choose one of these 3 things to go first, then one of the 2 remaining things to go second, and then whatever is remaining goes last. So there's 6 different ways that I can traverse a tree, but in general, we think of this as in order, pre-order, and post-order. And so it's just a matter of, and this is presuming I'm always going to go to my left before I go to my right, because you can see this, the other 3 is just if I go to my right rather than go to my left. And so the in order traversal, we can see this, is the way we go ahead and we print in order, right? This is just so everything would print in its sorted list. If I kept going to my left as far as I could, kept going, and then when I hit a null and I stopped, then I would print my value out, and then I would try to go to my right. And you go, this is where the idea of recursion fits in here. So it's one of those, it's better just to try it out than it is to discuss in a lot of this, because it's like trying to describe a lot of things. It's like recursion is difficult, right? So in order would be that, where I go to my left, then I process, I go to my right. Pre-order, process first, then go left, and then come back, and then go right. So it's tricky here. And then post-order is just left, right, and then process when I come back all the way. And so some of these, you're like, why do we care about some of these things? And so like for deleting the entire list, or my entire tree, I got to use post-order, because I have to make sure at a given node in my tree that everything to my left, everything that's down below me to my left is destroyed, everything to my right is destroyed before I come back and destroy myself. Because if I destroy myself first and then I try to go to my left, I'm going to crash, because the operating system was given back my memory of what I just deleted from myself, and that pointer will go off and cause a big issue. So we do use these in different ways. It's not like we're teaching these things to you just to teach you just for no reason. Okay, so for traversing a tree, so if I went in order, so let's just say talk about in order. I go to my left, I process myself, then I go to my right. So I go, okay, I start here at the root, and I try to go left, can't go left anymore, so I come back up and I print my 7, try to go right, and I can't. And then I come up, and now I'm here, I processed my left, so I print the 19, try to go right, and I can't. And so I come up now and try to print 31, and I print 31, and I try to go to my right, and I can now. And so now this node tries to go to its left, and this tries to go to its left, and then comes back up because it's null and says, oh, I'll print the 43, can't go right, so comes back up, prints its value, goes to the right, doesn't have anything to print. So at the end of the day, in order, printed out everything in this tree in sorted order. And that's what we're going for with in-order traversal. So let's say we have pre-order. Let's make sure pre-order means process first. So then I would print the 31, I'd print the 19, I'd print the 7, right? Because I'm process, then left, process, then left, process, then left, can't go, come back up, can't go, come back up, go right, 59 prints, try to go left, 43 prints, can't go left, can't go right, come back up, can't go right, come back up, done. And the whole thing traverses. And again, what order is that? That's pre-order. It doesn't have a real, it's not really ordered per se, but there is a very strict process, right? So it's and the post order is the same thing. It's like it's not in any particular order. If you were trying to say like it's half sorted, or I don't even know what you would say. It's not really ordered, but that's just the way we call it. So then the step at post order means go left, go right, and then when you come back finally, then print. So I go, okay, can't go left, can't go right, can't, come up, print 7, come back, try to go right, can't, come back, print 19, go to 31, now go to my right, so it's not printing 31 because I went to my left, now I got to go to its right and try to go left, can't, print 43, come back up, go right, can't, and now it's printing 59, and then it finally comes up because 31 finally fulfilled its purpose and deleted everything in its left, everything in its right, and now it's done, print 31. So again, post order is great for whatchamacallit here, for like deletion of the entire set, a linked list, I'm sorry, binary tree, because you notice at every point of the way, every node 31 is the last, because it's the last one, because it needs to be the last one because it's the highest up. And so 19 makes sure that the 7 was done before it, and the 59 makes sure that the 43 was done before that. So every step of the way, you can see that everything all of its children are deleted before it is. So everything kind of works from bottom up. So in this way, everything would be deleted in correct order. So moving on to searching the tree, we've already discussed this previously. So we start at the root node and we just basically ask the question, hey, are you the value I'm looking for? And just like the binary search, I go left and right depending on the answer. But this time around, instead of having numbers that go back and forth, if I hit a null, I didn't find it. If I find the value, I found it, of course. But if I hit a null, it's not in there. So trying to search for the 43 one more time, you go, okay, hey, 43, nope, I got to go to the right because 43 is larger than 31. And I say, okay, 43 is smaller than 59, so I go to my left, and there I found it. And now, how about 17? So something slightly different. So, hey, 31, okay, 17's less than, got to go to my left. And I go, okay, 19, 17's less than, got to go to my left. And I go, hey, 17's greater than, got to go to my right. I hit a null, it's not in there. And that'll work for every case, obviously. It will work for every single case. And in this kind of situation, since we're just using integer values, you could have a bool function that could just be like a true false. Is this thing in here? Yes or no. Hit a null, return false, find the value, return true. That's not very useful practically because in a real world situation, you probably have a binary tree full of pointers to things that are sorted in some way. And so, and that pointer is pointing to an object, a class that has a ton of data stored inside of it. And so I need to access that record instead of just going, oh yeah, integer, that's a simple case. But yes, if it's a pointer to a game object, be like, okay, now I need its position in space, and now I need to rotate it, and I need to do all these things. It would make sense in a larger application to be able to return an iterator or a pointer to the data value that's stored under there itself so that I can manipulate that data. Maybe not change its identification number because that's what keeps the thing sorted, but I should be able to get in and modify some of the records under the hood. So that is like a little more advanced topic, but that's the reason why we need to search this thing. Why do we have this thing in the first place? So we can have pointers to a whole ton of things and it's already sorted for me in some way. That was it for search. And so now deletion, that's where things can get a little tricky. And so when I go to do this video later, I'm going to have my little cheat sheet over here because it can get a little daunting because there's 3 different situations that can occur. And some of the cases, there's nothing illogical about the cases. I mean, you would do exactly like if I just gave you a piece of paper and I say delete this thing and show me tell me a series of steps that will make sure that whatever node I pick will be deleted. You would come up with the exact same structure. It's just, of course, writing this thing in code can be tricky, especially in something like C++ where there's pointers flying around all over the place. I mean, not that it's easy in any language. So if a node is going to be deleted from a leaf node, basically anything without children, well, there's really nothing difficult to do because because this one's only got one kid and we can't, child, and the child falls away. There's nothing left to maintain, so we just can fulfill. We've got to make sure to delete the node. We're always going to delete the node so we don't have a memory leak. But in this case, the 19 now points to null because there's nothing, there's nothing more outside of the 1. So now it's 0 points to null. So now if there's one child, so like, let's see. So if I was going to delete the 19 here, in this case, which has a child, I have to make sure all the linkages get to the right places so that I can delete the 19, but maintain 7 and any of its children and maintain the binariness, the binary tree rules of keeping everything correct. Because let's just see. If the node is to be deleted, has one child, adjust the pointer so that the parent of the node to be deleted points to the child of the node to be deleted, then delete the node. So that's a complete. This, like the 0 was simple, right? And this gets a little trickier, and you can imagine that the 2-child method gets trickier even. So, like in this case here, so let's see. I want to delete 19. So what do? What does it say? So delete and just the pointer says the parent of the node to be deleted. the third, in this case, I'm deleting the 19. My 19's parent is 31, and you got to watch out for this because it's not a doubly linked list. So the 19, I can't get back to 31 from the 19. There's at least with this structure, there's no pointer back. So I have to maintain the parent and the child as I go, and maintain all of these kind of structures, so that what happens is, let's see. So then, with one child, left or right, this pointer, which pointed to 19 previously, now needs to point to 19's child. This one needs to come around and point to 7, and then it doesn't matter what's going on, I can delete the 19. So I wish they kind of left the 19 in here, 31, or just have the arrow point to 7 in the same place, because maybe that's a little visual, because nothing moves around in memory, but it just feels like it is now that you're moving everything up. So again, what is happening with one child and one child only, whether it's on the left or the right, the link to the node that's going to be deleted is replaced with the link to its child. So the 31, instead of pointing to 19, will point to 7. Just like if I was going to delete the 59 here, since there's only one child, this pointer to 59 will now point to 43. So at the end of the day, maybe I discussed it poorly, trying to think it out and talk and do all this at one time, but it's not ridiculously complicated. It's just, I need to know the parent of the node that's going to be deleted. I need to know the node that's going to be deleted, and then I can have the child. And I just got to figure out if it's which one is it that needs to go into the place, because it could be 50-50 shot theoretically, right? It could be the left node, it could be the right node. Which node is it that needs to get replaced and get pointed to? So yeah, so 1959, so anything, so these are the only two cases that we can talk about with one child, at least right now, because this has 2 children, these have 0. So the 19 and 59 are the only ways, the only nodes that could be deleted using this methodology. And the 7 and 43 were previous, and then the 31, in this case, is the only node that could be deleted with 2 children. And I don't even think we described that more than just like a trust me on this, because this is the complicated one, as you could imagine, because it could be the left node, it could be the right node. What the heck do we do? So let's see, if there's 2 children, how would I delete the 31 and maintain a binary tree as everything got moved around to accommodate for that deletion? So let's see, if the node to be deleted has left and right children, promote one child to take its place, and then locate the correct position for the other child in the subtree to be promoted. And yeah, read the text, right? Or watch the next video. It's just saying, conventionally speaking, promote the right child and position the left tree underneath the right. And yeah, there is something here. So okay, good. Shoot, so I got to describe it, right? So okay, so it's better done than described, right? So let's see, I'm going to delete the 31. So the idea was promote the right child. So that's, so again, what am I doing? The 31 is going to go away, but the right child is going to be deleted, but then we have to adjust all the linkages underneath it so that, and in this case, the 43 needs to go to my left, and so the 59 becomes the root, in this case, or the root, 43 comes below it, and then we know that the 19 needs to hook into the 43. And so now, if you want to almost think about this, this is a singly linked list, almost a reverse singly linked list, because I have my 59, I have my 43, I have my 19, I have my 7. Everything is connected. Everything, my right pointers all point to null, but you notice, right? It's a straight line link, and this is just a coincidence the way this thing lined up. But this is the complicated case, and you really have to think it out, because there's more than just this one thing that can occur. But the amazing thing is, people have thought out, especially with the recursiveness of it all, they have made some really slick, simple code, a few lines of code that can handle this in every case. And it's better, again, the recursiveness is what melts the mind when it comes to doing all this stuff. So, okay, so we'll leave that for another time. If I butchered it, I butchered it. we'll move on to other things here. So let's see. The last topic here is templating. And so everything, again, we are dealing with in this video dealt with integer values. But of course, this std : set, std : multi-set, they are implemented as binary trees. You can use, they're generic, right? They're templated. So you can use anything you want, int, float, pointers, you name it. And again, next video will show all that cool stuff. We'll go through every detail, just like we have for the other collection types. So of course, it should be implemented as a template to be more flexible, because otherwise we would have to reinvent and create. Every time I want to create a linked list of a different type, I'd have to go in and change the types and create and have an int type and a float type and a bool type and a this type and a that type. Well, maybe not a bool type, but you get the point here. And so all the other stuff, once we've implemented this as a library, we only have to think about this once. It's like, why don't I have this all memorized? Why don't I have this memorized? Like, I could go in and figure it out if I had to. And this is the time of the year where I kind of have to step up and be a little better with my understanding of this deletion, especially with 2 children from a binary tree. But the reality is, as a programmer out in the field, it's just one of those assumptions, presumptions that you make. You understand how it works, and you can just get your job done, and you don't have to worry about those details. That's the greatness about using libraries, is you write it once or somebody writes it. You do not have to understand all those details. But again, this is year 1, year 2 of your education. It is very helpful to understand what it is doing, because maybe one day you're the one who has to go in and fix things up inside of those libraries, or you have to write a linked list, or you have to write a binary tree. Like, for some reason that the standard template library does not provide one for you in the correct way you need it. And so if you understand how these things work, you'll have a much easier time of getting in and making those changes. Because if you just don't understand, right, you just don't understand. Okay, so, and of course, all the other implementations, is one set greater than another? Is one set less than? Are they equal? What does that mean? Like, someone has to come up with those definitions, those relational operators, and all the other functionality, inserting, deletion, and algorithms that could basically partition these things and do all sorts of crazy things. There's a lot of cool stuff we can do. And again, it's in a library. Someone thought it up for us, so we can just implement it without having to think. And that pretty much covers the slideshow. So again, thank you for sticking with this high-level introduction to a binary tree. We'll have at least 2 more videos accompanying this. For me in my future, for you, you probably will be staring at this and not even realizing that it's my future. So, so stick with that, and thanks again. swardb@cod.edu is a great way to get a hold of me, or comment here on YouTube. And thanks again, and we'll see you in the next video.